Hello and welcome everyone to this second lecture in the vector series. In the last lecture, we saw what were physical quantities, the basic definitions of vectors. Also, we saw the differences between the types of physical quantities. Then we saw the different types of vectors, collinear vectors, coplanar vectors, and so on and so forth. Uh, After that, we ended upon the point that we were going to start the laws of vector algebra. So let's begin with the laws of vector algebra. So in physics particularly, there are three important laws of vector addition, I would say, that are quite helpful. Uh, First, before beginning the laws of vector algebra, first let us talk about an important point, which is multiplying a vector by a scalar, which was left out in the last lecture. So let's just quickly talk about that. So let's just suppose we have a vector like this. Let us name it a vector. Now, what is meant by multiplying a vector by a scalar is that suppose I have a real number lambda, and let's just assume for now that it is greater than 0, and by meaning to multiply this vector by a scalar, we just mean to scale it up or scale it down. So if lambda is greater than 0, so then if we multiply this vector a by lambda, we will get a new vector which will be either greater than vector a or smaller than vector a in length or magnitude, depending upon whether lambda is greater than 1 or less than 1. So if lambda is greater than 1, I get a new vector which is lambda times a vector, whose magnitude is in fact lambda times the magnitude of a vector. And if lambda is greater than 1, then obviously lambda times a vector is also greater in length than a vector. Obviously it is a scalar multiplication, so the direction of lambda times a vector is still the same as the direction of a vector. Now let's take the second case. If lambda is less than 1 but it is still greater than 0, so if lambda is less than 1, in this situation we will again get a vector lambda times a vector, but in this scenario the magnitude of this vector, that is lambda times magnitude of a vector, it will be less than a vector, which means this new vector formed lambda times a vector, in case where lambda is less than 1, its length will be smaller than the original a vector. Now but its direction will be still the same as that of a vector, because it is a scalar multiplication. Now the direction will only change in one scenario where lambda is less than 0. Now if lambda is less than 0, it just means that we are multiplying vector a by a negative real number lambda. So in that scenario, we'll still get let's say if this is vector b, and if we are multiplying this vector b by a real number lambda which is less than 0, so then we'll get a new vector whose length will be greater than b vector or less than that of the length of b vector, depending upon whether lambda is less than -1 or between -1 and 0. So let's take that two cases. If lambda lies between 0 and -1, so if lambda is between 0 and -1, so the new vector formed, which is lambda times b vector, first most point is that its direction will get reversed, because we are multiplying b vector with lambda and lambda is negative, so the direction of b vector will be flipped. In addition to that, its length will be reduced, as lambda is less than the magnitude of lambda is less than 1, because it lies between -1 and 0. So we'll get a new vector something like this, which will be exactly anti-parallel to B vector, which means its direction will be flipped by 180 degrees. Also, if lambda is between -1 and 0, then the length of this new vector formed will be less than the length of original B vector. And let's take the second scenario as well. If lambda is less than -1, if lambda is less than -1, then again the original B vector will be flipped. So let's see the new vector, which is lambda times B vector. So the direction of this new vector will again be that of the complete opposite of that of the original B vector. But this time the length of this new vector formed will be greater than the length of the original B vector, as lambda is less than -1, is even less than -1. That means the magnitude of lambda is the modulus of lambda is greater than 1. So that is just the simple concept of multiplying a vector by a scalar. Now let's come back to the laws of vector algebra. I hope you all of you guys understood this. Multiplying a vector by a scalar just scales its magnitude, or makes it greater in length, or shortens it depending upon the value of lambda. Also, if lambda is negative, then the direction will be flipped by 180 degrees. So now let us see what do you mean by the triangle of vector addition, which is the first law that we have to study in physics regarding to vectors. So if I'm given any two arbitrary vectors, let's say vector A and B in space, then in order to apply the triangle of vector addition, we first need to parallel shift any one of the vector so as to join it to the other vector. Now in this scenario over here, let's say vector B was lying over here and I parallel shifted it to its new position so that the tail of vector A and B coincide. But in order to apply the triangle of vector addition, I'll need to parallel shift them again, because in order to apply this law, I need the vectors in such a fashion that the head of one vector is connected to the tail of another vector. So let us say I parallel shift vector B again along the length of vector A so that I arrive to this new position. Now understand what I have done here. I have just taken this vector B and parallel shifted this whole vector along the length of vector A so that the tail of vector B now coincides with the head of vector A. So we reach this final situation where this is the head of vector A and it is coinciding with the tail of vector B. Now once we arrive in such a situation where both the vectors are arranged in such a fashion where the head of a vector is connected to the tail of the second vector, now we can apply the triangle of vector addition. So the triangle of vector addition says that if whenever we have any any two vectors arranged in this fashion, then the resultant of these two vectors can be simply found by completing the third side of the triangle. And that third side, the direction of the vector, the resultant vector, will be in such a way that it will go from the tail of the first vector to the head or the tip of the last vector. So I'll quickly draw that resultant vector. So this vector over here, R vector, represents the resultant of A vector and B vector. Now let us try to interpret this situation with an example. Let us say if I have a person A who is applying a force which is represented by A vector. Assume that this A vector is representing a force vector, and a person B is applying a force which is represented by B vector. Assume this B vector to be a force. Now if these two forces act simultaneously on a single body, then the body will neither act as if A vector was the force A vector was being applied on it, nor will it act if as if the force B vector was applied on it. It will act as if the force of the resultant vector was applied on it. So instead of acting as if the force A was acting on it alone, or the force B was acting on it alone, it will act like the resultant force is acting on it. So this was all about the triangle law of vector addition. Now let us see how do we write the mathematical equation of the triangle law of vector addition. So in order to do that, once we have completed the figure, uh, choose any one direction, either clockwise or anti-clockwise. Suppose for the sake of simplicity, I'll choose here the clockwise direction. So let us do that. I choose the clockwise direction. Now start from any one vertex. Let us say I start from this vertex, which is the tail of vector A. Now all we have to do is go along this triangle by traversing each of its sides, and while doing that, if we go along the direction of a vector from its tail to head, we take that vector as positive, while if we go from the head of the vector to its tail, then we count it as negative. So if I start here, I'm going along the direction of vector A, so I'll take it as plus vector A. After that, I'm going along the direction of vector B, so I'll again take it as plus vector B. And finally, while traversing the third side, I'm going against the direction of the resultant vector, so I'll take it as minus R vector. And this the sum of all these is always equal to 0 in a closed loop. Now if I'll just rearrange these, I'll get A vector plus B vector equals to R vector, which is the mathematical equation of the triangle law of vector addition. So now that we know what is the triangle law of vector addition and how do we apply it, let us see what is meant by the subtraction of vectors. It is very similar to the triangle law of vector addition, and subtraction of vectors is in a way very similar to the addition of vectors. Now let us see how that is done. Let us take the following scenario. Let us assume this is the x-axis while this is the y-axis. Now let us say that I have a vector, a vector, which is acting along the x-axis. I'll represent it like this. I hope all of you guys are able to see this. Let us say this is this is the a vector which is acting along the x-axis, and let us say this is b vector. So by applying the triangle of vector addition which we just learned, the resultant of a vector and b vector will be found by completing the third side of the triangle. So let us do that. Let us say this is r vector, the resultant of a and b. So the mathematical expression for this would be a vector plus b vector equals to r vector. Now what if I wanted to find out a vector minus b vector? Now let us see how that will be done. So we want to find out what is a vector minus b vector. Now this expression a vector minus b vector can also be written as a vector plus minus of b vector. So what we are doing in subtraction of vectors is that instead of subtracting b vector from a vector, we are adding the minus of b vector to a vector. Now let us see how this is done. Let us see how this is done. Now say again, if I take the same example, let's say this is the x-axis and this is the y-axis. Again I'll take the a vector as I took it in the previous example along the x-axis. Let us say this is the a vector, and in order to take the minus b vector, we just saw while multiplying a vector by a scalar, if we multiply it by a negative number, minus of b vector is just nothing but minus 1 times b vector. So if we multiply b vector by a negative number, its direction will be flipped. And as we are multiplying it by -1, its length will exactly remain the same as that of the original b vector, just its direction will be flipped. So now let us get back to our example. In order to indicate minus b vector, it would be similar to the b vector that we indicated in the previous example, just that its direction will be completely opposite. So this vector with its head on this side and tail on this side represents minus b vector. Now the resultant of these two vectors would represent a vector plus minus of b vector, which is nothing but a vector minus b vector. Now again applying the triangle law of vector addition, the resultant of these two vectors would be calculated just by completing the third side of the triangle. Now how do we determine the direction of the resultant vector? Now in order to determine the direction of the remaining vector, there is a trick. Whenever there is subtraction of vectors involved in the triangle law, and among the two shorter sides of the triangle, if one of them is the negative one, then the other shorter side has to be the resultant of the remaining two. I'll repeat that again. While applying the triangle law of vector addition, if there is subtraction involved, and if one of the shorter sides is the negative side, then the other shorter side has to be the resultant of all these three vectors. So for a vector over here to be the resultant, the third vector must have been in such a fashion. So if I name this as r vector, so applying the triangle law in this triangle now, I'll choose any one direction, whether clockwise or anti-clockwise. Let us say if I choose the anti-clockwise direction this time, I'll start from any one vertex. Let us say I start from the origin. So I'll go in the anti-clockwise direction now along the sides of this triangle, while using the points that if I go along the direction of a vector, I'll take it as positive. If I go against the direction of a vector, I'll take it as negative. So the first side is vector a and I'm going along its direction, so I'll write it as plus a vector. The second side is b vector minus b vector, I'm going against its side, against its direction, and so I'll write it as minus of minus b vector. And lastly, I'm going against the direction of r vector, so I'll write it as minus r vector. And the sum along a closed loop is always 0. Now if I rearrange this, I get so now we again end up with the same result, r vector equals a vector plus b vector, and that is actually correct because we started by stating that r vector equals to a vector plus b vector, and as I mentioned, the sum of all vectors along a closed loop is always 0. So no matter how many times I reverse the direction of any of these three vectors, when I apply the triangle law of vector addition, I'll always end up with the same result, r vector equals to a vector plus b vector. I hope all of you understood that point. Now let us move ahead to the next concept, which is the parallelogram law of vector addition. Now let us see what does this law tell. What does this law tell us? So let us suppose again I have any two arbitrary vectors in space. So I'll take again a vector and any other vector, let's say b vector. So the first step remains the same. We have to parallel shift any of these two vectors such as their tails coincide or their heads coincide. But for the sake of simplicity, let us coincide the tails. So let us say I parallel shift b vector to its new position over here so that the tail of a vector and b vector coincide. Now the parallelogram law of vector addition says that if we again parallelly shift both of these vectors in order to complete a parallelogram, then the resultant of these two vectors is given by the longer diagonal of the parallelogram hence formed. So let us see how that is done. So if I take B vector and parallel shift this B vector along the length of A vector, then I'll get another vector. Let us see how that is done. So I take B vector and parallel shift it along the length of A vector in this new position. So let us say this is the B vector that I parallel shifted along the length of the A vector, and I take the second vector, which is A vector, and parallel shift it along the length of B vector to its new position. So let us do that. So let us say this is the A vector which I parallel shifted. So this figure hence formed will be a parallelogram, and the resultant of these two vectors, A vector and B vector, will be given by the longer diagonal of the parallelogram. So let us do that. Now by saying the longer diagonal, I mean that the diagonal, the vector along the diagonal whose start point is the tails of the two vectors that we joined. So in this case, this middle vector will be the resultant of these two vectors. So let us call it R vector. Now let us try to interpret this situation. If let's say a force is acting along A vector, let's say some guy is pulling along A vector, and another guy is pulling along B vector, uh, and these two forces are applied on a same object. So the object will move as if it was pulled by the resultant force, and it will move along the direction of R vector. Now let us try to build up on that by taking an example. Let us say if there is a block lying on the floor. Let us say this is a block lying on a floor, and let us say if two persons are pulling this block. uh, let us say one person is pulling this block with a force of F1, and I'm representing this force by a vector F1 vector. And let's say another second guy is pulling this block with a force F2, and let's say these two guys are pulling this block with force F1 and F2 respectively. Now let us quickly apply the parallelogram law of vector addition on the forces F1 and F2. So I parallel shift the vector F2 along the length of vector F1. So I get something like this. And then I parallelly shift the vector F1 along the length of F2 in order to complete the parallelogram. Now the longer diagonal of the parallelogram, or the diagonal passing through the vertex where the two original vectors were coincided, that is our resultant. So let us say this is our resultant vector. Now understand one important point. The two guys were pulling the block by the forces F1 and F2. So if let's say the force F2 was absent and only one guy was pulling this block with the force F1, then the block would have moved along the line of action of force F1. I hope all of you guys remember what is the meaning of line of action from lecture 1. So if the force F2 was absent and only one guy was pulling it with the force F1, this block would have moved along the line of action of the force F1. Similarly, if the first person was absent and only the second guy was pulling the block, then the block would have moved along the line of action of force F2. But because both of these forces are acting together, the block will neither move along the line of action of F1 nor along the line of action of F2. It will move along the line of action of the resultant force, that is in this direction. So the block moves along the line of action of the resultant force. I hope all of you guys understood this example very well. We'll get into the formulas of the parallelogram law of vector addition in the upcoming later videos. Let us now move on to the next law of vector addition, which is called as the polygon law of vector addition. Now let us see what does this law say. I'll explain this by taking again an representation. So let us say I have something like this. Uh, Let us say I have a system of vectors. Uh, Suppose this is a vector, and let us say I have another vector, b vector, and the head of a vector coincides with the tail of b vector. Let us say I have another vector, c vector. Again, the head of b vector is coinciding with the tail of c vector. And let us say I have another vector, d vector. Again, the head of c vector is coinciding with the tail of d vector. And the polygon law of vector addition says whenever we have a series of vectors, that is many vectors, arranged in such a fashion that the head of a vector is coinciding with the tail of the next vector, head to tail, and so on. And no matter how many vectors there are, the resultant of all these vectors is given by a single vector going from the tail or the beginning point of the first vector to the tip or the head of the last vector. So in this case, this r vector would be the resultant of all these vectors. I'm sorry for the figure, but this r vector would obviously be a straight line completing the polygon, which is this many-sided figure. Now, one point to note, and it is a very important point, that no matter how many forces are there, and no matter in what direction they are acting, as long as they are connected in this fashion, such as the head of one vector is connected to the tail of next vector, as long as they are connected in this fashion, the resultant would always go from the start of first vector to the end of the last vector. Now, I'll elaborate more on this by taking another example. Now, let us see this example quickly. So, I have many vectors connected in that similar fashion where they are in continuation. The head of a vector is connected to the tail of next vector. I have a1 vector, a2 vector, a3, a4, a5, a6, and a7. Now, we'll just simply follow that law. What that law said was no matter how many vectors they are, and no matter what direction they are connected, as long as they follow the pattern, the resultant will go from the start of the first vector to the tip of the last vector. So let us quickly draw the resultant. So this is the resultant vector of all those forces. So I wanted to highlight an important point. The resultant can also cut the individual vectors. It is possible, it is absolutely fine, it is absolutely normal. The resultant would still act in this same way following the law. Now, once we have understood what the polygon law of vector addition says, let us see how we get to that law, how it is derived. So the derivation is very simple. We simply use the triangle law of vector addition to derive it. So I'll derive it quickly. Let us say I have a system of vectors again. Uh, Suppose this is a1 vector and this is a2 vector. Similarly, this is a3 vector, and so on. And I have a n-sided polygon. So the last vector will be uh, the resultant vector. But let's say I have an n-sided polygon in which all the vectors are connected in our in the manner of continuation, where the head of a vector is connected to the tip of the next vector. So in order to find the resultant vector, we apply the triangle of vector addition. Now let us see how that is applied. Let's say if I have let's consider the first two vectors, a1 vector and a2 vector. Now these two vector, let us assume these two vectors to be the two sides of a triangle. So by the triangle law of vector addition, the resultant of a1 and a2 vector would be given just by completing the third side of the triangle, and it will go from the start of the first vector to the tip of the last vector. So let us quickly draw the resultant. So this is the resultant vector, which is equal to the sum of the first vector and the second vector. Now if we consider the resultant vector and the third vector, now these again form two sides of a triangle. So we can also apply the triangle law of vector addition here. So if we consider these two sides, again the resultant would be found by just completing the third side of the triangle, which is this vector. Now this vector would be just r vector and plus a3 vector, and r vector itself is the addition of a1 and a2 vector. So the second resultant vector equals to the first resultant vector plus the next side of the polygon, which is the a3 vector. Now similarly, we see the pattern in this. The two adjacent vectors get added to form their resultant, and their resultant is again added with the next side of the polygon to form the next resultant. If we keep on doing this, we reach to the last vector, and the last resultant is equal to the sum of all the sides of the polygon. So we can simply write that in a one equation, which is a1 vector plus a2 vector plus a3 vector plus and so on till the second last vector, because last vector will be the resultant of all the sides, will be the last resultant vector that we will calculate. The last side of the polygon would be the last resultant vector that we calculate using the triangle law of vector addition if we go one by one, completing all the sides of the polygon. So till the second last vector, so addition of all sides of the polygon till the second last vector, that would be equal to the last vector. Let us say that is the an vector. So an vector, the last side, would be the resultant of all these vectors, and the direction of an vector, the direction of the resultant vector, would be just opposite to the direction of the trend of these other vectors. So if the other sides are following an anti-clockwise sense, an anti-clockwise fashion, then the resultant or the last side would be the resultant of all these vectors, and it would have an opposite direction, that is a clockwise direction. So the last vector would be something like this. So this would be the last vector, an vector. It will have an opposite sense, and it would be equal to the addition of all other vectors. Now if we take the an vector to the other side of the equation, we get a1 vector plus a2 vector plus a3 vector plus and so on plus an minus 1 vector minus an vector equals to 0. Now if we shift an vector to the other side of the equation, we get this result. Now let us try to interpret this result. So in this second equation, we have minus an vector, which would simply mean flipping the an vector, keeping its magnitude or the length same, but just flipping its direction. So if we flip the direction of an vector, it will be same as the direction of other vectors which were opposite to the direction of an vector. So an vector, if we flip it, it will then follow the direction of other vectors. So then if we go around the sides of the polygon, it will just form a closed loop. So this second result says that if the direction of all vectors is same, and if we go around a closed loop, then the sum of all those vectors is just equal to 0. So that is why I said in the triangle law of vector addition, the sum of vectors along a closed loop is always 0. So I hope all of you understood this result. So another important point, while writing the JEE mains and advanced examination, you need to get familiar with some mathematical symbols. So I'll just quickly write this second result using the mathematical symbol of summation. So we get this. Now, I hope all of you guys know how to interpret the summation symbol. If not, I'll explain. Now, the summation symbol just means that for all terms A with the subscript I, we have to add them one after the other, and the limits of the summation show the values that I will be taking. So I is going from 1 to n minus 1. So this will mean a1 plus a2 plus a3 till a n minus 1, which is written in the above statement, which is the second equation that we got, and minus an, that completes the equation, which is equal to 0. So I want all of you to get familiar with this notation, as it is used quite a lot in JEE papers, and many students don't know how to interpret symbols like this. So that is why they are not able to solve the questions. So get familiar with symbols like this as much as you can, so that on seeing the questions in the paper, you are able to solve them very easily. Now, after we have seen all these laws, let us also quickly see two important points about vectors. So the first important point is that a vector addition is commutative. Now I'll explain what do I mean by that. First, I'll just write the statement. Now, it would seem as a pretty straightforward statement, but it has a lot of significance. Now, what does the commutative law say us? It tells us that if I add b vector to a vector, it would be same as adding a vector to b vector. So, no matter how I do the addition, it will always give me the same result. Um, I'll explain more on this. I'll talk more on this by taking a representation. So let us say I take any two arbitrary vectors in space, a vector and b vector, and I parallel shift on all them to join them in the manner of continuation. Let us say we have arrived at this situation. Now we can apply the triangle of vector addition, which simply says that if two sides represent the two sides of a triangle, then their resultant is found just by completing the third side. And the direction will be from the start of first vector to the tip of last vector. So let us quickly do that. Uh, this is the resultant vector, and r vector will be equal to the sum of a vector and b vector. Now let us parallelly shift a vector along the length of b vector. So I parallel shift a vector along the length of b vector. So I get something like this. This is the new position of a vector, and let us parallelly shift b vector along the length of a vector. So I'll complete the figure. So we would get something like this. Now let us try and apply the triangle of vector addition in both of these triangle forms, the upper triangle as well as the lower triangle. So let us quickly choose a direction. I'll choose the clockwise direction over here. So in the first triangle, the lower half, I'll start from this vertex right over here. So I get a vector plus b vector minus r vector equals to 0. I'll write that quickly. Plus a vector plus b vector, and then against the direction of the resultant vector, so minus r vector. equals to 0, as the sum in a closed loop is 0. Now I'll rearrange this to get a vector plus b vector equals to r vector. So this is the first result. Now let us try to apply the triangle of vector addition in the upper triangle, upper half. So let us start from this vertex, the same vertex. I get again b vector as I'm going along the direction of b vector. Again plus a vector as I'm going along the direction of a vector. Minus r vector as I'm again coming against the direction of r vector while traversing the upper half. Again the sum along a closed loop is 0, so equals to 0. Now if I rearrange this second equation, let us see what do I get. B vector plus a vector equals to r vector. Now just observe the left hand side and the right hand side of these two equations. The right hand side is the same, that is the resultant vector, whereas we can see the commutative law, the commutative nature of vectors in the left hand side. No matter if you add b vector to a vector or a vector to b vector, the resultant will always be the same. Now let us see another important property of vectors, which is the associative nature of vectors, the associative law. Again, it is very simple. Let me first write the mathematical statement for it. Now, this law simply says that if we have three vectors and we are adding it, it doesn't matter which two vectors we add first. The result will always be the same. So if I add the result of b vector plus c vector to a vector, or if I add the result of a vector plus b vector to c vector, it will always give me the same result. Now let us try to understand this by taking a representation again. So let us say if I have any arbitrary a vector and I'll take another b vector and I'll take a third vector c vector. Now notice one point, I am taking this vector, taking these vectors so that the head of a vector coincides with the tail of the vector, or tail of the next vector. I am doing so because we need to add these vectors and make use of the triangle law of vector addition. So I am assuming the vectors already in the continuation manner. So now let us look at the LHS of this equation. We need to calculate the sum of b vector and c vector first. So let us focus on b vector and c vector in our representation. So again they are in a manner of continuation, and we can apply the triangle law of addition of vectors on b vector and c vector by assuming them to be two sides of a triangle. So again, the result by a triangle of vector addition, the resultant of these two vectors would be found just by completing the third side of vectors, the third side of the triangle. So the resultant would be something like this. I'm sure all of you are able to see this. The resultant of b vector and c vector would go from the start of the first vector, which is the b vector, to the tip of the last vector, which is the c vector. Now, as we have calculated the sum of b vector and c vector, now we have to add this sum to a vector, which would simply mean taking the resultant of a vector and this resultant vector that we have calculated from b vector and c vector. So if we add these two vectors, the a vector and the resultant of b and c vectors, again we can apply the triangle of vector addition. So again a vector and this resultant vector are in continuation. We can assume them to be two sides of a triangle, and so the resultant of these two vectors would be again calculated by completing the third side of the triangle, going from the start of first vector, which is the a vector, to the tip of the last vector, which is the b plus c vector, or the resultant that we calculated. So let us quickly draw the resultant. So the resultant would be something like this. The final resultant vector is the sum of A vector plus the sum of B vector and C vector. So this is the resultant, final resultant vector if we added B vector and C vector first and then added their sum to A vector. Now let us also try to interpret the right hand side of this equation by again taking a representation. Let us again take a similar representation. We'll take an A vector, then we'll take a B vector in a similar way, and we'll again take a C vector in a similar way. Now, according to the right hand side of this equation, we need to add A vector and B vector first. We need to calculate the resultant first. So let us concentrate on A vector and B vector in our representation. Now again we can apply the triangle law of vector addition here as they are in a manner of continuation, and the resultant will be calculated by going from the start of the first vector to the tip of the last vector. So let us quickly draw that. So the resultant would be drawn something like this. This resultant vector is the sum of A vector and B vector. Now that we have calculated the sum of A vector and B vector, then we will add it to C vector. So now that we have calculated the resultant of A vector and B vector, which is this bracket right over here, then we have to add it to the C vector, which is this vector over here. So now let us concentrate on this resultant vector and C vector. Now again we can apply the triangle law of vector addition as these two vectors are in a manner of continuation. So the resultant of these two vectors would be again found simply by completing the third side of the triangle, going from the start of the first vector to the tip or head of the last vector. So let us quickly draw the resultant. So the resultant would be something like this. We first added A vector and B vector, and then we added their sum to C vector. And if we observe closely, the resultant in first case is similar to the resultant in second case. In fact, not similar, it is exactly the same. This just proves the associative nature of vectors. No matter if we add B and C vector first and then add their sum to A vector, or if we add A and B vector first and then add their sum to C vector, it would always give us the same result. So now that we have seen some important properties regarding vectors, I guess this much theory is enough. Now let us quickly look at a very interesting and um, uh, a very beautiful question. So let me quickly write down that question. So this is the question. Let us see what the question is saying. A car is moving along a circular track with constant speed of 20 meters per second. So it has a constant speed, but remember it is moving along a circular track. So no matter if the speed is constant, its velocity will be changing at each and every point, as velocity also depends upon direction. And the direction of the car, if it's moving along a circular track, will be changing at each and every point. So hence the velocity will be changing at each and every point, but the magnitude of velocity will remain the same, which is nothing but the speed of the car, which is 20 meters per second. But the overall velocity will be changing at each and every point. So the car is moving along a circular track with constant speed of 20 meters per second. And at different times, at different instants, the car is at point A, point B, and point C. So the arrows just represent the direction of its velocity at that particular instant. So what do we need to calculate is the change in velocity, the velocity change in going from A to point C and in going from A to point B. So what was the change in velocity of that car when it went from point A to point C and from point A to point B? So let us quickly see how this is done. You can pause the video here for some time and try to solve this on your own. Okay, now let us see how we will solve this. I'll again draw the figure over here. So notice one important point. The points A and C are diametrically opposite to each other. Also, the tangential arrow represents the direction of velocity at that particular instant. So let us say the car is at A and it has a velocity VA. So the direction of this velocity at this particular instant is along this particular arrow, which is shown over here in a tangential direction. Now let us see the first case. So we need to, in the first case, we need to find the change in velocity, which is delta V. Delta is the symbol used to represent change in a quantity. So delta V, change in velocity from point A to C. Now, let us consider the velocity of the car at point A to be VA and the velocity of car at point C to be VC. Now, if the points A and C are diametrically opposite, then the velocities VA and VC must be 180 degrees apart, which means they should be completely opposite. So we need to calculate the change in velocity from in moving from point A to C. So that will be nothing but change in any quantity is calculated just by uh, doing final value of that quantity minus initial value. So we just have to do final minus initial in order to calculate the change of something. So the final velocity was at point C, which is VC, and minus the initial velocity, which is VA. But notice one point. Uh, if we take a direction to be positive, let us say the direction of VA, which is rightwards, is positive. So let us make our own scale over here. This is the positive direction and this is the negative direction. And if it is not given in the question which direction to assume as positive and negative, uh, the first starting point, the direction of the vehicle at starting point should be assumed as positive because we are asked to calculate the change in velocity. So let us quickly see how that is done. So change is final minus initial. So final is the velocity at point C, which is VC, minus the initial velocity, which is at point A. But the direction of VA should be taken as minus of VA in this equation, because if we are considering VC as positive, so if we are considering VC as positive, VA would be negative as it is completely opposite to the direction of VC. So this scale is always relative. It will change according to each and every question and we can assume it according to ourselves. So if I assume the direction of VC to be positive, the direction of VA would be negative. So if I have to subtract VA from VC, I would do VC minus of VA. Now, it is a very important point to understand about the relative direction. In kinematics, we would come across this very often. In each and every question, which direction is positive and which direction is negative will not be given. We just have to assume a certain direction to be positive and then do our calculations accordingly. And the answer would always be correct no matter which direction you would assume as positive. As long as your calculation and your concept is correct, the answer will always be correct. So if I assume VC to be positive and VA to be, so VA would automatically be negative as it is in the completely opposite direction. So delta V from in going from A to B would be final, which is VC minus VA, because VA is opposite. So now let us substitute the values. Now the speed of the vehicle was given to be 20 meters per second and it is constant. So let us substitute that. So on substituting the value of the speed as 20, now the speed is the same. So the speed of the vehicle at point A and point C would be the same, as we are taking the direction into consideration by uh, putting the signs along with the values. uh, we have already taken care of the direction, so now the only remaining part of the velocity is the magnitude that we are substituting over here as 20, because it was given the speed of the vehicle is 20 and speed is nothing but the magnitude of velocity. So we get the change as 40. Now let us try to understand what does this 40 change means. The change is 40 meters per second. Now if you are traveling along the direction of VA with 20 meters per second, to go in the direction of VC with the same speed, you first need to cancel these 20 meters per second and then increase 20 meters per second in the opposite direction in order to achieve the state of VC. So that is the change. So first you need to zero the initial velocity of 20 and increase in velocity of 20 in the other direction in order to achieve the state of VC. So that signifies the change of 40 meters per second, and that is the change in velocity. Now let us solve the second part of the question, which is to find the velocity change in going from point A to B. Now let us do that quickly. Now in order to calculate the change in velocity from point A to B, we would have to apply the triangle law of vector addition. So let us quickly do that. Again, this VA is a vector. The velocity of the vehicle at A is a vector, any arbitrary vector in space. And the velocity of the vehicle at point B, let us say it is VB, is a vector, arbitrary vector in space. Now let us parallelly shift these two vectors so that we can apply the triangle law of vector addition. Let us do that quickly. Now in order to do that, we need to first arrange them in a manner of continuation. Let us parallelly shift vector B so as the tail of vector B coincides with the head of vector A. Let us do that. This is our VA vector and this is our VB vector. I have parallelly shifted vector B so as they are in a manner of continuation. Now in this figure, we can apply the triangle law of vector addition. So let us quickly do that. Now as we can see over here, the vectors VA and VB form two sides of a triangle and their resultant would be simply calculated by completing the third side of the triangle. And the direction of the resultant would be from the start of the first vector to the end of the second vector. So let us quickly draw the resultant. So the resultant vector would be something like this. And remember, these vectors were tangential. So when I parallelly shifted VB vector so as to connect to VA vector, this angle formed over here would be 90 degrees. The magnitude of VA and VB both is 20 meters per second, as that is the speed and it is constant. Now we end up with a triangle. Two of its sides are 20 meters per second and it is a right angle triangle. So in order to find the magnitude of the resultant, we just simply need to apply the Pythagoras theorem. So if we do that, the magnitude of R vector would be equal to the Pythagoras theorem basically. So under root one side square plus another side square. So this would come out to be root 800. So now let us try to interpret this result. The units obviously would be meters per second. So the calculation part is very easy and anyone can do that. Now let us actually try to feel the result, to interpret the result. So the vehicle was first moving along VA with 20 meters per second. After that, it changed its direction along the course of the circle. It changed its direction so that it started moving along VB. So in order to bring about this change, there has to have acted some sort of a vector quantity, some sort of quantity on that vehicle, some sort of a force or anything like that. So that is represented by R vector. R vector is that quantity which brought about this change in the direction of this vehicle. Now R vector can be provided by anything. So the vehicle is moving in a circle, so it could be the cause of its centripetal motion. So it could be anything, but R vector is that quantity which brought about the change in the direction of vehicle from the direction of VA to VB. So R vector is the change in velocity of the vehicle from point A to point B. So whatever is the magnitude of R vector, that is nothing but in fact the change in velocity from point VA to VB. So delta V from A to B is nothing but root 800 meters per second. I hope you all understand this. Now, this is the formal method of solving the question. Now, I'll tell you a short trick that we can use to solve these type of questions in which change in any quantity is asked. So, let me quickly share that trick with you. Now, there are many questions framed in JEE mains exam and advanced where we need to find the change in velocity of a particle. Firstly, it was going in some direction, then it changed the direction due to any factor, and we are asked to calculate the change in its velocity. Now, there is a very quick trick in order to calculate the answer instead of doing all this. So we just need to apply a simple formula. Let's say we are supposed to calculate the change in velocity of a particle. So that would be simply delta V, which is the change in velocity. It always equals to 2V sine theta by 2. Remember this formula, it is very important. Whenever in any question we are asked to calculate the change in velocity of anything, we can simply apply this formula instead of doing all this calculation. So the change in velocity would be 2V sine theta by 2, where theta is the angle by which it got deflected, or by the angle by which it changed its direction. So I'll now use this formula to solve this question again. So the vehicle was first moving along VA, then it started moving along VB. So the change in angle was 90 degree. It changed its direction by 90 degree. So theta over here would be 90. So for this case, the change in velocity would be 2v, and v over here is the speed of the particle, which is 20, sine theta by 2. Let me quickly do that. So let us quickly do this. 2v sine theta by 2, and theta in our case is 90 degrees. So let us quickly substitute that. And as we know, sine 45 is 1 divided by root 2. Now, if we shift this 20 inside the square root sign, we will get the following result. As you can see, we again arrive to the same result as we did when we used the proper method. So we can use this formula. It is very important formula. Whenever we are asked to calculate the change in velocity, and these type of questions are literally asked a lot in exams in maybe or JEE mains, advanced or CET. So just use this simple formula instead of doing all this. So we again arrived at the same result. So I hope you have noted down this formula. So that is all for this lecture, guys. Let us quickly go through it once again and see what we learned. We first saw what is meant by multiplying a vector by a scalar. We saw how the direction is flipped if the value of the multiplying scalar is negative. We also saw how it scales up and down the length of the vector. Then we moved to laws of vector addition. We first saw the triangle law of vector addition. We saw how to get to its mathematical form by going around the loop. Then we saw the subtraction of vectors by using triangle law of vector addition. Then we saw how the result won't change because around a closed loop it is always the sum is always the same. Then we saw the parallelogram law of vector addition, how by parallelly shifting the vectors we can complete a parallelogram and the resultant would be always the longer diagonal of the parallelogram. Then we applied it to an interesting example and saw what would be the resultant effect on the block if two forces are acting. Then we moved on to the polygon law of vector addition. We saw no matter how many the forces, the resultant would be always the last side of the polygon taken in an opposite direction. Then we just saw an interesting case of the polygon law of vector addition where the resultant was cutting the individual vectors and it didn't matter, the result would still remain the same obeying the law. Then we derived the polygon law of vector addition. We derived its equation. We saw how it is derived using the triangle law. And then we just learned a new notation. It is actually quite general notation. We interpreted the final result. We then saw some properties regarding two vectors. The commutative law, we saw how it is derived using the triangle law. We derived these two equations and verified that the commutative nature of vectors holds. Then we saw the associative nature of vectors. We evaluated both sides of this equation and saw that the result would still remain the same. Then we solved an interesting question and we calculated the change in velocity. And yeah, you can see. And we, apart from calculating it from the general method, we also used a short trick in order to get to the answer quickly. So that is all for this video, guys. I know it was a long video, but I'm sure you learned a lot from it. Thank you very much.